All right. So yesterday we wrapped up chapter 7 on steady state error, and I actually forgot to show you this MATLAB code. I'll upload it. Basically just showing the difference between type 0, type 1 systems and then applying different inputs to it. Um, so I just want to go through this real quick. And then today we'll continue on with root locus and keep chipping away at chapter 8, which is root locus, until we finish. Anyway, so here we have multiple transfer functions, and maybe I'll run it line by line, kind of like bisection. So we can, yeah, let's do that instead. Simulation. Okay, so here we have a type 0 system. So G0 here is type 0. If we look at G0, you can see that it's a first order system with a pole at -2, no poles at the origin. And then I use the feedback. I use the command feedback, which creates a closed loop feedback loop. This one here is, it automatically assigns it as negative feedback. So if I look at T naught, we're going to have, yeah, a closed loop feedback system, which is that. And then if we look at type 1 now, where we have G1 now, we have this system where we have a pole at the origin and a pole at -2. If I look at PZ map of G1, we could probably see. Oh, it's taking a long time to plot. Wow, okay. Anyway, you can see right here, it's kind of hard to see. Maybe I can expand this plot out. It's kind of hard to see, but you can see that there's a pole at, now that did not make it better. There's a pole at the marker. There's a little tiny X at the origin, a little tiny X at -2. So that's a type 1 system. So then when we look at the feedback of the system, we get that. And then to run my simulation parameters, we're basically have a time span here. And then this is going to be my step input, meaning that I just have a constant value. And then for ramp input, the nice thing about ramp input is we can just use our time span as a ramp input, because a ramp grows linearly with time. So, and this is a unit ramp input. If I want to make it not unit, I can just multiply by some number like 2 or whatever. And then now I do I simulated using LSIM with step and ramp, and then I have my inputs here, and then we'll just run this whole thing. All right, so let's look at here. If we look at type 0 system for a step input, so here in orange, it's going to be the orange line is going to be our desired line, or kind of like red orange. This red line is the error. And so to find the error, what I did was I just did input minus output, and I plot the error line. And then the blue line is the output. So this is our type 0 system for a step input. So then therefore, for a type 0 system with a ramp input, we now get output is going to be increasing slower than the input, meaning that the error is going to grow with it. So as time goes to infinity, error goes to infinity. And then think for type 1 system, kind of similar story. If I put this is a type 1 system, so we have a pole at the origin for the open loop transfer function. We have our input command, which is 1. That's what we want to be at. Output is going to be this transient response, and it converges to 1. So you can see error drop down to 0. And then, which tracks because type 1 system have 0 steady state error for a step input. And then here we have a type 1 ramp input. So here we're seeing, right now it looks like the output and input are diverging. It's because the transient response hasn't decayed yet. So orange is our desired, blue is our actual output. So maybe to see a bigger picture, what we have to do is we have to increase our time scale to 100. So instead, I'm going to modify this code. I'm going to type in t end is equal to 100, and then I'm going to put t end here, and then put t end here as well. So automatically adds the iterations, and hopefully that works. So sometimes if simulation isn't working out, maybe we can expand the time scale. So it still looks like it's off. Something wrong with this ramp input. It looks like error is increasing. Um, Let me just check if I'm using T naught ramp input for T1, ramp. T-span. All right, well, it looks like I might need to do a little bit of diagnosis. Y ramp 0. Yeah, I'm looking at, I think I might have had something. Y ramps. Oh, yeah, I'm using the type. I should be using the type 1 system. Yeah, I never did the simulation for the, or I think I did. That's weird. Oh, there you go. Y ramp 1. Yeah, like you said. So T step 1. Yeah. So maybe if I were to change this to Y ramp 1, let's do that. There you go. Yeah, that looks right. This error calculation is actually using the wrong error calculation. So it should be, yeah. So I need to update this code. U ramp. There you go. Let's try that. There you go. Now you can see that error is constant and our lines are parallel. Our output and input lines are parallel, meaning we have steady constant error. There you go. So I'll upload this code. All right. So yesterday we were talking about root locus. Basically, I think to recap, uh, when we're looking at this closed loop transfer function and we pull the gain out of the open loop transfer function. The closed loop transfer function, the poles of the closed loop transfer function is going to contain the open loop poles, which is DGDH, and the open loop zeros, which is NGNH. And then to control or to move the closed loop poles to a different position, we change K. So then we talked about the definition here of root locus. It's a graphical technique that gives a qualitative description of a control system's performance. Basically, what we're seeing is just the pole locations, like the trajectory of the pole locations on the pole zero map. And then so like this is a useful visualization tool, and it's going to be the foundation for chapter 9. So then we went to this example here in the textbook where they have a model of a security camera system where we have the motor plus camera modeled as K2 over S times S plus 10, and then the amplifier, which is K1, and then we combine K1 and K2. And in this instance, maybe the motor plus cam, the K2 is fixed. So then maybe we can just change how much we amplify the signal. So then that's how we control the gain K. And then here, what I did here was we found the closed loop transfer function, or I gave it to you, and then I'm showing you different values of K and writing down different values of the poles based off of the Ks. So one thing about, actually, I'm gonna add one more point just to drive this point home. So gain K is equal to 40, we get minus 5 plus 3.87J. And minus 5 minus 3.87J. And then when you have a gain of 50, I'm going to use a different color. This is going to be the final value we're plotting. It's going to be minus 5 plus 5J and minus 5 minus 5J. So basically what we're doing is we're just plotting or we're finding different values of we're taking different values of k, evaluating different values of k, and finding the pole locations for those corresponding gains. And then now that we have a bunch of values for the poles, what we're going to do is we are going to draw the pole locations on the PZ map, which is the plot on the left side. So I got this green is going to be our starting point here, which is gain of 0. So we have two real poles, one at the origin, or that's not a real pole, but let's say pole at the origin and the real pole at -10. And then when we increase the gain to 10, we're going to get -8.87 and -1.13. I'm just eyeballing it. So this is k is equal to 10. And then at k is equal to 15, we get -8.16, which just barely moves, and -1.84. So two real poles again. So I'm going to say that's k. K equal to 10. This is k equal to 15. And then when we go to 25, when we have two repeated poles, real repeated poles, I'm just going to overlap them right here. This is k is equal to 25. So what we're seeing is as I'm increasing k, we're seeing these two real poles get closer and closer on the real axis. And then when I increase k past 25, it actually branches off into the imaginary plane. So now it branches up and down. So the poles go up and down to -5 plus 2.24 and -5 minus 2.24. And then when I increase it even more to 40, I get -5 at 3.87, -5 plus 3.87, and -5 minus 3.87. And then finally, when I increase it to gain of 50, we get -5 plus 5 and -5 minus 5j. So basically what we're seeing is we're seeing these two poles on the real axis approach each other. And then when they become repeated, increasing gain makes them break apart into the real and into the imaginary plane. So that's what changing k does. So we're changing the pole. These are the closed loop pole locations that we're changing. So the root locus plot just basically draws the trajectory. So we show the starting point, which is 10 and 0, -10 and 0. And then we draw this line here. Basically what we're showing is we're having the two poles go this direction. And usually we draw arrows to indicate the direction they're going. You don't have to, but it's just a good visual for yourself. And then they break off like this. So they branch off. So basically what we're showing here on the root locus plot on the right-hand side is the trajectory of the poles as k is increased. So what we're showing here is the trajectory of the closed loop poles as k increases. One thing that is very nice about this visual is that we can tell that this system will always be stable because the poles always stay in the left half plane, the closed loop poles. No matter how high I increase the gain of the system, the poles will always stay in the left half plane. One thing you can also note is that as k increases, your percent overshoot goes up as well. And our damping ratio goes down. And this just has to do with the fact that the poles here is related to the damped frequency, which is equal to omega n times no, it's actually omega n multiplied by 1 minus zeta squared. And then on the real axis, this corresponds with the imaginary axis. And on the real axis, it's going to be minus omega n times zeta. A few other notes about this is that we have no way of knowing which pole, like the pole at -10 and the pole at 0. We don't know which one goes up and which one goes down. But the nice thing is that this is symmetric. So if one goes up, one's going to go down. It's going to be symmetric about the real axis. So no way of knowing which pole goes up/down. The other thing is that based on the root locus, we know these three facts. One, from 0 to k equal to less than 25, the system is overdamped. Actually, it should be k greater than 0. System is overdamped because we have two real poles that are not unique. At k is equal to 25, the system is critically damped. And at k greater than 25, the system is underdamped. And when you look at this plot, you can tell that the system will never be undamped. It'll always have some damping. Because this root locus plot never passes the imaginary axis. These points are 90 degrees, and later on we'll be able to determine the angles of these breakaway points. So one last thing is, and I'm going to define these formally, but this is called a breakaway point. It's the point where the poles go from real to imaginary. And these will be defined more formally later on. Are there any questions? So this is the basics of what a root locus plot is, and we'll be talking about how we draw this in the coming sections. All right. So in order to draw this, we're going to just review a little bit. You might know this already from 564, but we're just going to review a little bit about complex numbers, phase, and magnitude. When we have a system, a function represented, or it's in the complex domain. Here I define A as a constant number in the real domain, but in this case though, f of s is in the complex domain, so we usually use this C, like the C with this little vertical bracket going through it, mainly because s is in the complex domain, because it's represented in the frequency domain. And the frequency is the imaginary component. Okay, so we want to evaluate s at a real number plus an imaginary component, and we want to find the polar form. So basically to do that, I sub in F at real plus J omega. I get the real part plus J omega plus A. And then I'm going to separate it by the real part, which is going to be sigma plus A in parentheses, just to show that these two are grouped together, plus J omega, which is the imaginary part. And then now when I draw this on a complex plane, where I have my imaginary component, I have my real component, then this point here is going to be the real component, sigma plus A. And here we're going to assume that A is positive. And then this part is my frequency component. All right. So now that we have that, we know that we can determine the angle of this. And then the length of this is just the magnitude of F evaluated at that point. And our angle here is, so in this textbook, we're going to reference the positive x-axis. So the positive x-axis, I'll write out positive. Positive x-axis is the reference point. So for instance, if I were to have a point here, or maybe down here, we would reference it like this. So then to find, so our Cartesian coordinates will be this. Sigma plus A, and then omega. That's how we represent it in Cartesian coordinates. But with polar coordinates, we'll represent it like this. F evaluated at sigma plus A. So that's going to be basically my radius, and then angled, like this little angle with theta, and theta is going to be typically expressed in radians. Degrees is also okay as well, but out of good habit, I would just use radians because your calculators are default. Usually your calculators are default in radians unless you have to set it. And when you plug stuff into MATLAB, it's going to be, when you use cosine or sine, it's going to be in radians. If you want, you can use cos D or sine D. That's going to be in degrees. And so to get the magnitude, F, it's going to be the square root of the real part squared plus the imaginary part squared. So the real part of F squared plus the imaginary part of F squared, which is going to be equal to, maybe I should write this better. Magnitude is equal to that, which is going to be equal to the real part, which is sigma plus A squared plus omega squared. Then to get the angle is just going to be the arctan of the imaginary part divided by the real part based off of our graph here, because we're doing the height over the length, which is equal to the arctan of omega over sigma plus A. So one thing I want to note about this is that, let's say you want to, when we're referencing the positive x-axis, we want to account for the quadrant that the angle is in. So let's say down here now, let's say this is minus sigma plus b now, where b is positive. Or let's just do minus b here. And this is just omega, minus omega. Nah, sorry. I'm going to do minus sigma plus a. I'm going off script right now. So then here, our magnitude is going to be the same, but then our angle is going to be arctan of minus omega divided by minus sigma plus a. So the negatives are going to cancel out, and we get this. We still get the same angle, omega over sigma plus a. So these two are the same mathematically, but the quadrants are different. Quadrants are different. And this will actually be important for drawing the root locus. We need to identify the quadrant. So identify the quadrant. So for this one, I'm going to call this theta 1 and theta 2. So then theta 2 is just going to be equal to theta 1 plus 180 degrees or pi. Or if we're doing it in radians, or theta 1 plus 180 degrees if we're doing it in degrees. So identify the quadrant that the angle is, that this point that's being evaluated at, and then that's going to be your angle. So this is important because mathematically, if you plug into your calculator, you see something different from the quadrant, you usually just have to add 180 degrees or pi. Any questions? So is it applicable if it's only 2 quadrants away? What do you mean? Like, oh yeah. So let's say if it's in the 4th quadrant, the angle. So if you want to, and actually maybe I need to note one thing is that positive when theta is greater than 0, that means we're measuring counterclockwise. Okay, so then to answer your question about so I'm digressing a little bit, but to answer your question, when theta is less than 0, we're going clockwise in terms of measuring it. So then when we're when we are, let me leave that like that. So if we have an angle like this, we can either measure the angle like that, where theta is going to be less than 0, or if we measure like that, maybe I'll use a different color. We measure like that, theta is going to be greater than 0. And then in terms of the angle, right, if you do tan inverse of, this is going to be a positive number. So let's call it B now, and then but maybe a negative imaginary number. Your calculator, I don't know what it'll spit out. It'll either spit out it's most likely going to spit out a negative number. So then if you want to turn it positive, you can either add 360 degrees to it, or you can yeah, because then if you have a positive number, then your calculator is going to reference this angle instead. So like if you're in quadrant 4, but then the calculator gives you an angle that's in quadrant 2, but you know it's in quadrant 4, add 180. But if it gives you a negative number, you can use the negative number or you can add 360. They're both the same as well. I'm not sure if that answers your question, but I think I might have digressed a little bit, but it just made you just reminded me of this the negative angle because in quadrant 4 your calculator will usually give you a negative angle. I don't know if all calculators will do that. So I'll draw like that. Maybe I'll make it a side note. I'll make some space here. Maybe I'll do it like that. Theta. And I'll do, yeah, like that. So, like to get comfortable with this kind of stuff, it's just going to be on the homework where you just draw the root. I'm gonna have you all draw the root locus, and you'll get a feeling of you'll get a feeling of like what quadrant to put it into, and yeah. So, yeah, I'll give you some tips on identifying the quadrants and which quadrant to stick to later on. So one other thing is, so in this example we did, we basically just drew the polar coordinate or found the polar coordinates for 0. So then for a polar coordinates of a pole at the same location, the trick is actually pretty straightforward because if we were to, we're looking at a pole now. So if we were to write this out, we get this 1 over sigma plus a plus j omega. So then if we multiply the top and bottom by its conjugate, we get this sigma plus a minus j omega, and we get sigma plus a squared plus omega squared. Okay, so the magnitude is going to be the same. The reason why I wrote it like this is because then we can break it up into its real imaginary components. So sigma plus a, so this is the real component, over sigma plus a squared plus omega squared minus omega times j. So this is the imaginary component of sigma plus a squared plus omega squared. So when we take the magnitude of it, it's going to be the same. It's going to be the square root of the real, it's going to be the square root of the real component squared plus imaginary component squared, which is going to be equal to square root of sigma plus a divided by sigma plus a squared plus omega squared squared plus omega squared. In this case, it would be, yeah, it would just be omega squared over sigma plus a squared plus omega squared. And basically, we can just rewrite it like this. You might see a pattern now. Sigma plus a squared plus omega squared divided by sigma plus a squared plus omega squared, close brackets squared. I don't need a line that long. All right, so these two cancel out because they're the same terms. And we just get square root of 1 over sigma plus a squared plus omega squared. All right, so to no surprise, this is just the magnitude of this is just the inverse of the previous example we did. It's just the inverse of that. So when we have a, so then the nice thing about this property is that when we take the phase of it, it's going to be the arctan of minus omega. So because the imaginary components, the imaginary component here is going to be, all right, I'll write it out fully. It's going to be minus omega over this whole term here, sigma plus a squared plus omega squared, divided by sigma plus a over sigma plus a squared plus omega squared. So then these two will cancel out, and we get this. Inverse tan of minus omega over sigma plus a. So basically, it's just going to be equal to, yeah, it's going to be equal to that. We're going to get a negative angle. Guess to show you the difference. So we just did F1 of F, let's call F1 of S is equal to the pole, or is equal to the S plus A, which is a 0, and F2 of S is equal to 1 over S plus A. I'm going to call M1 is the magnitude of F at S at sigma plus omega. And theta 1 is going to be tan inverse of omega over sigma plus A. Then M2 is just equal to 1 over M1. And theta 2 is equal to minus theta 1. That's the relationship. So I guess to stack it, I'm going ahead of myself because this goes into chapter 10. If I were to define a transfer function and I call it S plus B over S plus A, and I were to find the magnitude of G at evaluated at S is equal to J omega, right? So G at J omega is just going to be equal to the magnitude of the 0 of all the zeros combined, which is going to be B squared plus omega squared divided by A squared plus omega squared. And then the angle of G is just going to be the angle of the zeros minus the angle of the pole, which is going to be equal to tan inverse of, or the arctan of omega over B minus the arctan of, oh man, I'm running out of space. I'll move this over. Minus arctan of omega over A. So this is a really, really useful relationship because instead of flipping the angle, you just subtract the angle because of this minus sign. We subtract any values, like any poles we have, we just subtract that angle. We find the angle of the pole, then we subtract it. So a little bit digression. You'll see more in this. This is more in chapter 10, but it relates to what we're doing now as well. Okay, so to formalize this, uh, so if we have a transfer function, so I showed you an example of just like a single pole and a single zero. So if we have some transfer function and we are able to factorize it into a bunch of poles and zeros like this, you can find the magnitude and phase of this transfer function at some point S in the complex plane. So we can, so as a reminder, S is going to be some real number plus J omega. Typically for Bode plots and Bode plots, which is in chapter 10, we only look at S is equal to J omega, and we ignore the real part. We just get rid of that real part. We only evaluate the frequency response. We only care about how the system responds to frequencies, and we don't care if it decays because we assume it's stable already. So so what we do is we evaluate the magnitude of each zero evaluated at S, and we multiply it. So this is the product notation. So that's the magnitude. And then the phase is going to be the sum of all the zero angles minus the sum of all the pole angles, which is defined here. And then we evaluate the angles relative to the real axis and rotate in the counterclockwise for positive. If you go negative, rotate clockwise. I would just stick with one direction. It just keeps things simple. For positive angle measurements. But if you want, you can go negative. You can measure it negative and just go clockwise. Okay, so yeah, I guess why do we care? We need this information for compensator design. If we want to design a PID controller, we need to know how to calculate these polar representation. And we use this method for frequency analysis, which is in chapter 10 as well, which is probably the most important chapter in this textbook besides PID controller design. I have an example here. Find the magnitude and phase at S is equal to -2 plus J for the system here. I think we'll finish that today. And then, yeah. So we're going to finish this example. Okay. So first thing I'm going to do is I'm going to decompose this. I'm going to factorize this polynomial equation, this S squared plus 2S plus 5. It's going to be a pair of complex conjugate poles. So we get S plus 3 divided by S plus 4 times S plus 1 plus 2J, and then S plus 1 minus 2J. Just to make a note here, this S plus 1 means it has a real part at -1 and a imaginary part at -2 and a real part at -1 and a +2. So just note that this plus sign means it's a minus real part for the pole location. Then we let S is equal to -2 plus J. So then we get G of -2 plus J is equal to. So I'm going to sub in the -2 plus J in the numerator, and we get 1 plus J in the numerator. And then we get, let's see, sub in -2 plus J, we get 2 plus J times, be -1 plus 3J times -1 minus J.
So then the magnitude is going to be equal to, so the magnitude of the numerator is going to be equal to 1 squared plus 1 squared because of the 1 in the real part and the 1 in the imaginary part, divided by the square root of the real part squared, which is 2 squared plus 1 squared times the square root of minus 1 squared plus 3 squared times square root of minus 1 squared plus minus 1 squared. Which is equal to 1 over root 50. Or 1 over 5 root 2. So that's the magnitude evaluated at that point. All right, for the, question. Can you simplify? Oh, like cross them out? Yeah. Yeah, you can do that. Like these two can just, like that? Oh, yeah, you could do that. If you want, actually, if you want to just skip all this and you want to just plug in g at minus 2 plus j, you get, I'm not sure if this will be easier. I just like to, um, I just like to write it out. You can plug in minus 2 plus j into s squared times 2 times minus 2 plus j plus 5 as well, and just find the magnitude of that as well. I'm not sure if that will be easier, but if it is, you're welcome to do that. And then you just take the magnitude of that multiply component, magnitude of that, and the magnitude of that. Personal preference. Yeah. So then for finding the angle, I think visually it'll make more sense. So I'm gonna draw out this point we're evaluating to. And basically what we're going to do is I'm going to show you what it looks like. So we have 2 here, 2j minus 2j, and it's at a location of minus 1. And then we have a second pole at minus 4 and a 0 at minus 3. Let me draw this. It's not going to be spaced linearly. And let me draw the pole locations first. So we got one at minus 1 plus 2j and the pole at minus 1 minus 2j, and then a 0 at minus 3. And we're evaluating to minus 2 plus j, which is going to be right here, roughly, right there. This is s is equal to minus 2 plus j. And basically what we're doing is we're just taking the angles of all of these, and we're either adding or subtracting it, depending if it's a polar 0. So, like I said, the reference point is going to be the x-axis, positive x-axis. So this is, I'm going to call this one theta 1, call this one theta 2. Let me call this one theta 3. And then I'll call this one psi 1 to differentiate the angles of the zeros. And note that it's all going to be referenced like that. It's always from the positive x-axis, always to the right of the pole or the 0. Like that. All right, so
All right, so it's actually 11:20, so we'll just finish this up tomorrow. All right, thank you.